Hello everyone, it's me, Blake again, here to go over the concepts relating to biostatistics that you'll need to know for your exam. In this video, we'll discuss the difference between sensitivity and specificity, how to calculate relative risk and odds ratio, as well as the pertinent information relating to confidence intervals. So with that being said, let's go ahead and get started. Now that we've discussed survey errors, we can expand our discussion to sensitivity and specificity. Let's take a look at the data in this image. The left half of the image represents the region of the data that is actually positive, and the right half of the image represents the region of the data that is actually negative. Meanwhile, everything inside of the circle represents the data that is tested positive. So let's take a look. Any data that is actually positive and has tested positive, we can call true positives. Any data that is actually negative but tests positive because it's inside the circle is a false positive. Meanwhile, any data that is actually positive but tests negative is considered a false negative, and any data that is actually negative and also tests negative is considered a true negative. The balance between these values can be described using sensitivity and specificity. Sensitivity is the true positive rate, or the probability of a positive test result given that the individual truly is positive. Specificity, on the other hand, is the true negative rate, or the probability of a negative test result given that the individual truly is negative. Let's go ahead and visualize this by drawing out a table. On the left-hand side, we have those who test positive and those who test negative. On the top, we have those who have the outcome and those who do not have the outcome. First, we have true positives, or TP, and this describes someone who has the outcome and tests positive. It can help if you think of the outcome as having COVID, for example. Next, we have false positive, or FP, and this describes someone who does not have the outcome but tests positive. Next, we have false negatives, or FN, and this describes someone who has the outcome but tests negative. And finally, we have true negatives, or TN, and this describes someone who does not have the outcome and tests negative. Sensitivity, which is the true positive rate, is the percent among those with the outcome that test positive. Its formula is given as the number of true positives divided by the total number of those with the outcome. Specificity, which is the true negative rate, is the percent among those without the outcome that test negative. Its formula is given as the number of true negatives divided by the total number of those without the outcome. An ideal test has both high sensitivity and specificity, but there is always a trade-off between the two. Let's go ahead and practice this with an example. Let's say that we have these values in our table. Our sensitivity, or true positive rate, is the number of true positives, 27, divided by those with the outcome, which is 27 plus 3. This gives us a sensitivity of 90%. Our specificity, or true negative rate, is the number of true negatives, 42, divided by the number of those without the outcome, which is 42 plus 18. This gives us a specificity of 70%. Next, let's talk about relative risk and odds ratio. The relative risk ratio and odds ratio are both used to measure the medical effect of a treatment or variable to which people are exposed. This effect could be beneficial from a therapy or harmful from a hazard. Risk is measured by taking the number of people with the outcome divided by the total number of people exposed to the treatment. Odds, on the other hand, is calculated by taking the number of people with the outcome divided by those without the outcome. Now, how exactly does probability and odds differ? Let's say that we have a 6-sided die. Let's compare the probability and odds of getting an even number when we roll the die. In order to calculate the probability, we take the number with the outcome, which would be the 3 even sides, divided by the number of events, which would be the 6 total sides of a die. This makes the probability of rolling an even number 1/2, which makes sense. Meanwhile, in order to find the odds, we take the number with the outcome, which would be the 3 even sides, divided by the number without the outcome, which would be the 3 odd sides of the die. This makes the odds of rolling an even number 1-to-1, as opposed to the probability of 1/2. Now let's discuss the risk and odds ratio. In order to calculate the risk ratio, we take the risk in the exposed group divided by the risk in the control group. Odds ratio is calculated by taking the odds in the exposed group divided by the odds in the control group. Odds ratio is high yield on your exam, so make sure that you know this formula. Now I understand that none of this makes much sense until we do a practice problem together. So let's go ahead and take a look at this example here. In this case, the risk of the treatment group is the number of people in the treatment group who have the disease divided by the total number of people in the treatment group. This is 90 divided by 300, which is 30%. Now the risk of the control group is the number of people in the control group who have the disease divided by the total number of people in the control group. This is 100 divided by 500, which is 20%. The risk ratio then compares these two values by dividing the risk of the treatment group divided by the risk of the control group, which is 1.5. This means that the risk of disease amongst those exposed to the treatment is 1.5 times greater than the risk of disease amongst those unexposed. The risk ratio, or sometimes called relative risk, can range from 0 to infinity, with 1 being the null hypothesis, which states that the risk of disease among the exposed and unexposed is the same. If the risk ratio is greater than 1, this means that there is more disease among the exposed than unexposed. This means that the exposure could be a risk factor or risk predictor for the outcome. If the risk ratio is less than 1, this means that there is less disease among the exposed compared to the unexposed. This implies that the exposure is likely a protective factor or protective predictor for the outcome. Let's do the exact same thing, this time for odds ratio. The odds of our treatment group is 43%, while the odds of our control group is 25%. The disease odds ratio is 1.72, which means that the odds of disease among the exposed is 1.72 times greater than the odds of the disease among the unexposed. And finally, the last concept that we'll be discussing in this video is confidence intervals. Recall that study results are based on samples, and sometimes these random samples can have variability. Therefore, we define a confidence interval, which is a range of values around our estimate that is expected to contain the true value. The size of the confidence interval conveys how precise we believe our estimate to be. A large confidence interval indicates greater uncertainty about the estimate, which suggests difficulty in making precise conclusions based on that sample alone. Your desired confidence level is usually 1 minus the alpha value that you used in your statistical test. So if you use an alpha value of p is less than 0.05 for statistical significance, then your confidence level would be 1 minus 0.05, which equals 0.95 or 95%. Let's say that our risk ratio of 2.25 has a 95% confidence interval of 0.5 to 3.9. It would then be written as follows. The 2.25 refers to the point estimate for the risk ratio. The 95% refers to the fact that we are 95% confident that the true risk ratio lies within the confidence interval, which has a range of 0.5 to 3.9. All right, everyone, that sums up the concepts that we'll be discussing in this video, so let's go ahead and wrap it up with a couple of example questions. Which of the following is true regarding confidence intervals? We have option A, the width of confidence intervals decreases with increased sample size. Option B, the width of confidence intervals increases with decreased standard deviation. Option C, the width of confidence intervals increases with increased sample size. And option D, the width of confidence intervals is independent of standard deviation. And the correct answer for this question is option A, the width of confidence intervals decreases with increased sample size. So as the sample size increases, the width of confidence intervals tends to decrease. Recall that the confidence interval captures variability due to sampling. Increasing our sample size means that we can get a better reflection of our population, making our sampling more precise, resulting in narrower intervals around the point estimate. Next, we have question number 2, which asks, in a study assessing the effectiveness of 3 new lasers, researchers calculated the following confidence intervals for their performance in tissue ablation. What conclusions can be drawn from these confidence intervals? We have option A, buy laser A, B, buy laser B, C, buy laser C, and D, don't buy a laser. And the correct answer for this question is option B, buy laser B. Now, these confidence intervals represent the estimated effectiveness of 3 different lasers in tissue ablation. Each confidence interval consists of a point estimate, which is 7.5 in this case, and a range of values, which is the interval, that are likely to include the true effectiveness of the laser with a certain level of confidence. All 3 lasers have a point estimate of 7.5, suggesting similar average effectiveness in tissue ablation according to this study. However, the confidence intervals differ in their widths and exact ranges. Laser A has the widest confidence interval ranging from 5 to 10, while laser B has the narrowest confidence interval ranging from 6 to 9. Overall, laser B may be considered the most consistently effective based on this study's findings, followed closely by laser C, while laser A's effectiveness is less certain due to the wider confidence interval. Alright everyone, I really hope you enjoyed revisiting these topics relating to biostatistics. In this video, we learned about the difference between sensitivity and specificity, we learned about relative risk and odds ratio, and we finished off with confidence intervals. That's it for this video, but don't you worry, I'll be seeing you in the next one.